Here's how we do the calculations. And our job will be first to calculate the average height, then we'll find the initial velocity, and then finally we'll find the time to reach the apex for the two hoppers below. So we'll be going through these calculations, and what you should do is try it out first, so you'll have to pause the video, and then when you're ready, go to the next slide and you can progress through the slides in that manner. So you give it a shot first, and you can see if you match what the presentation shows you. And what do we have here? We have the large hopper, and we did 5 trials, and this is how high they went. And then we did the small hopper, and we had 5 trials. So first let's calculate the average height. Here's the average height, which was calculated by adding these 5 together and then dividing by 5. And notice we don't have to put units in the table. Why? Because we have them up here. So for each data entry, we just put the number. Now, calculate the initial velocity for both hoppers using the third kinematics equation, and move on when you've given it a shot to check your answer. The third kinematics equation, so we're trying to find v0, the initial velocity. So we're going to isolate that, okay? So the first thing we do is put v0 squared all by itself, and we do that by subtracting 2a delta x from both sides, and then v0 is then the square root of v squared minus 2a delta x. So let's do the large one first. V squared, that's the velocity at the top, that'll be 0, then minus 2, and here's our acceleration. It's negative g, or negative 9.8, and the average height was 0.65. You carry out the math, and the large hopper we're calculating as 3.57 meters per second, and that's a little over 8 miles an hour. Now let's do the small one. Same thing, except we had a different height. It didn't go as high, so you would expect it perhaps to have a lower velocity, and yes, it does. We'll keep one extra significant figure here. We're actually only allowed to have 2. That's the limits of our measurements, but we still want to find total time, so we're just going to keep this intermediate step until we get the total time. Use the first kinematics equation to find the time to apex. So give it a try, and when you're ready, move on to the next slide. Using the first kinematics equation, the velocity at the apex is 0. Right? It goes up like this and comes down. Right here at the apex, the velocity is 0. So the first kinematics equation, solved for t, reduces to negative v0 over a. So let's work with the large hopper first. We already calculated the initial velocity was 3.57 meters per second. So we plug that in, and notice the negative sign over here cancels out with the acceleration, which is negative. It's down, negative 9.8 meters per second squared. And we get the time to apex for the large hopper was 0.36 seconds. Do the same thing for the small hopper, and that was 0.25 seconds. It got there quicker. And just kind of neat that just by measuring something with a meter stick, we can find its velocity and also the time it took to get to the peak of its trajectory.